Hello and happy Septandy! Last year for Septandy I did something a bit different. I started a series where I resurrected a game that I started in high school. And then that series kind of evolved into a new series where I made changes and improvements to that game that I started in high school. And that series has kind of grown and grown and continued and has become the through line for this channel. So this year, by doing something different again, I will deviate from that thing that was different a year ago and do something that's not directly related to the game. In fact, it's kind of the same as what the channel was before Septandy, because before Septandy last year, the channel was kind of like a bunch of different things, and then the different thing I did for Septandy that year was to focus the channel into the same thing. So I'm going to do the same thing this year as last year, which is to do something different. And in this case, that different thing is the same thing that the channel was prior. Hello and happy Septandy. Today we're going to investigate how to automate our debugging experience while using MAME. And we're going to do this in two ways. First, we'll talk about breakpoint actions and watchpoint actions, and how you can get the debugger to do something on your behalf in an automated fashion every time a piece of memory is written to or read from, or every time a breakpoint is hit. And then we're going to move on to number 2, which is an even more powerful way to automate your experience, where MAME has exposed many of its internal objects for your benefit. You can script them using the Lua programming language. And we're going to introduce how to do that and write a little script to do some fun things while debugging. All of the code that I'm showing you is available for download, so check the link in the description and you can play around with it yourself. And also a big thanks to Matt Greer's blog. Matt Greer has a blog where he talks about working on a Neo Geo game using MAME. And it was a good introduction for me to using Lua to script MAME. So I have links to his blog in addition to links to the MAME documentation for Lua as well. So take a look at the description if you're curious to investigate further. But without any further ado, let us go. The MAME debugger already has some built-in support for automation. It's just a bit limited, but you can use it for some useful stuff. And just as an example, let's have the debugger do something every time that BASIC is ready to accept new keystroke. So for example, it might occur right now, and then after I hit one key and it's ready for the next keystroke, we might have it do something at this point, and then do something at this point, and then this and this and this and this and this. The point in the ROM where that occurs is here at A1, B1. So right when we're ready to accept something new into the BASIC interpreter, we hit here, and then we go to this subroutine which takes care of blinking the cursor. We check the keyboard, and if it's empty, we go back up and blink the cursor again. So we're going to have a breakpoint right here before we enter that loop that cycles through the colors. So we could set a breakpoint at A1, B1. But what we'd like to happen is for the debugger to do something automatically, not for it to be this interactive thing where the breakpoint gets hit and that I got to do something and then I go back into the debugger. Instead, I want the debugger to do it all. I like the debugger to print some state for me every time that happens, and then to continue. The breakpoint command, I've just been using this section of it, but it continues on. You can have it be a conditional breakpoint, which only gets hit if this thing is true. And the part that we're interested in today is some action it can perform automatically without me having to tell it every time. And what I'd like it to do is print the value of the frame, which frame we're on, and also to print the beam Y. So this will tell me what frame it's on and where in that frame it is it's rendering at that point. This is not something you can easily determine from within the CoCo itself. This is where an emulator is very handy. So for the command, rather than just doing BP A1, B1, I'm going to do this. Stop at A1, B1. This is the condition, and I just have it set to 1, which means the condition is always true, which means every time you hit that instruction, stop. And then finally the action. I'm going to ask it to print the frame and the beam-y values. So within MAME, I can specify the names of registers like S, A, B, X, Y, and the debugger is nice enough to include these things as quote-unquote registers that I can print as well. So this will print the word frame followed by the frame number, and then the word beam-y followed by the actual beam-y location. And the thing that is really what's all about automating is this thing at the end. After I've printed go, G just says go from that breakpoint. So now the debugger isn't even going to stop, at least not visibly to me. It's just going to print it and then move on until it gets to that breakpoint again. Now, although I won't be demonstrating this today, you can do the same kind of thing also with the watch point command. You can use the watch point to stop whenever a particular memory location is read to or written from, and you can also have it perform an action automatically on your behalf. So the breakpoint has been set, but nothing has happened because we haven't hit A1, B1 yet. So watch what happens as I start typing into the CoCo. Every time I hit a key, it has hit the breakpoint, it has printed the things that I wanted, and it has continued. Now what if I wanted to do some analysis on this? What if I wanted to see, all right, what's the typical delta in frames if I'm typing really fast, or does the beam-y happen to be at around the same location? If I wanted to do that, I would need to do some processing on these values. Unfortunately, the debugger doesn't really offer me a full programming language where I can do anything complex. It's quite simple, and as you can see, getting code to run is really just a matter of adding an action to a breakpoint. Now you might be thinking, no big deal, just select it, copy it into a spreadsheet, and you can do some analysis, but have you ever tried selecting? This is what I'm doing right now. Click, drag, nothing, you can't select. But surely you can copy to the clipboard, you say. And yes, if I right click, I can copy what's visible to the clipboard. So only the part of the window that's showing can I copy, but I can't copy the rest of it. It's a very odd limitation with the debugger. So if all you need is some kind of logging, and you're just going to use your eyeballs to read that logging, and that's enough to help you, then good enough. But if you need a real language and the ability to write real code to do some processing and things, then you need to take it a step further. Now, before we go any further, I should warn you that what I'm about to show you, although it's fully documented, this is also subject to change. So all of these APIs that I'm going to be talking about could be different the day that you happen to be watching this video. So always refer to the latest documentation and be prepared to make tweaks as needed. The MAME developers have provided a way to expose many of the innards of MAME out to us, the users, where we can write scripts to automate those innards of MAME. And they use the Lua programming language to do that. Lua is a scripting language that hosts can choose to incorporate in the program, and it provides a way for users to automate that program. Think of it as an alternative to something like JavaScript. And the MAME developers have gone through the process of exposing a bunch of their internal classes so that you can automate it using Lua. The first thing you need to do is to get Lua actually running. So the way I'm choosing to do it is by having a script that I pass on the command line to MAME. So I've created this script here, and by using -script, that tells MAME to run this script as soon as MAME starts. There's also an interactive console. I'm not going to be using that. I tend to prefer doing all of my editing in a file that I can save, and then just running that file over and over again. To start with, I'm just going to have a simple one-liner script. So all it's going to do is to print a little message, print the name of the application, and the version. In order to do that, it's using this emu top-level object. Emu is actually an interface, and it's just always available. So you can type emu dot and then the name of the method that you want to call. I found that the documentation isn't always complete. For example, a couple of the methods I'm calling aren't actually in the reference section of the documentation, but they are part of this interactive tutorial that they have on the primary page of the Lua scripting documentation. In fact, much of the code that I'm showing you is based on that tutorial. So let's see what effect this statement has when I run it. You'll see that in my console window I have Lua says and then the name of the application and then the version. And then otherwise, MAME is just going to run normally. Next, we're going to print the state of the CPU. Here's how we're going to do it. We start with another top-level object manager. That's the MAME machine manager. And from that, we're going to go to the machine property. That provides access to the running machine object for the current session. From there, we go to the devices property. That returns what's called an enumerator that goes over all of the devices that are attached to the machine. I happen to know that the device that I really want to have access to has this tag, main CPU, so I'm explicitly doing this. But you could also iterate through the devices and print them using a technique similar to what I'm about to show you. So now that I've done this, the CPU object is placed into my CPU variable. And then I can go into that CPU and go to the state. State is a property on any device that exposes some kind of register state interface. In the case of the CPU, this is going to show me all the registers on the CPU. So to iterate through all of those entries, I can call pairs, which will give me the name value pair for each entry in that collection. And then I can have a for loop that goes through each of them and prints the tag. So I grab the tag and the value out of the pairs of tags and values, and I just print those tags. So this should be printing for me all of the names of the registers that MAME understands to belong to the 6809. And if we look here, we'll see we have cur_PC and cur_flags, and the PC register itself. Don't exactly know what the difference here is. And then we have all of the usual registers we would expect to see. Unlike the debugger, which is very nice to expose things like frame, beam Y, beam X, we don't seem to have that here on the CPU device. So what other devices do we have that we can interrogate? I can add another loop, but this time I iterate through all of the entries in manager machine devices. And I get a pretty long list. At least in terms of how things are organized in MAME, every one of these things is considered a device. You'll notice we also have a screen device, we have a VDG device. Unfortunately, their states are empty, so they do not have quote-unquote registers for things like beam Y and frames like we were able to get from the debugger. Things start to get interesting when I add some overlay graphics on top of the CoCo emulation itself. I can create my own function here which draws an overlay on top of the screen. If I have a reference to the screen, I can call this method drawBox. It gives me a chance to send it the corners and then the color. The FF here is the alpha, and then we have the RGB, so this should be about a cyan color. And this is the fill color, so since this is 0, the alpha is 0, so it's just going to be a transparent center with a border. But I'm going to need a reference to the screen object. There we go. So I've got some great code, but no one is going to call this. I need this to be called whenever the frame is ready to be redrawn. So to do that, I need one more line of code here. This tells the emulator to register my function with the frame done event. When the frame has been rendered, call my function drawOverlay. And this just gives a name for that registration. And there's my box. Now if I get the emulation going, that box will stay here no matter what happens inside the emulation of the CoCo. Now maybe we can do something a little more informative in our overlay. So in addition to drawing a box, let's put a message inside. This message will write the word stack, and then using the hex format, the value of the S register. So we haven't started the emulation yet, so it's just sitting there at 0. And here it is, kind of very subtly flicking between 7F2A and 7F2 something else. And if I move over to the debugger window, I see 7F2A and then occasionally 7F22. So in theory, these should both basically be in sync. Now, what if I wanted to do something similar to what I was doing with the debugger before? What if I want to know how far we are down the frame, what the beam Y is, every time that we're ready to accept a new character? So something that would refresh itself every time I press a new key. What I'd like to do is to add something to this print statement, kind of like this. So this will concatenate a new line into the text that I'm printing, and it will print some kind of value that I've set that tells me the time that was captured, the percentage of the frame that was remaining that I captured when the key was pressed. So I somehow have to get this variable set every time we're ready to accept new characters into the basic interpreter. Well, it just so happens that the screen object does have a way to capture the time until v-blank. So if I do this, then on that screen object, I'm calling the time until v-blank start method. This will return to me how long until v-blank occurs. Now this is returned in the format of an atto time. An atto time is a high precision time interval. We want to convert this into some kind of unit that we'll understand. And there just so happens to be a method on atto time that will convert it into a double, which is a number of seconds. So this is going to be a fraction of seconds. So I can expect this will be something like 0.001732, something like that. At least that's comprehensible, but it's still not very useful. If I multiply that by 60, then rather than this being a number of seconds, it will be a number of frames. But again, this is still going to be really a fraction of one frame, because it's very unlikely that the time until v-blank is going to be more than one frame. I don't quite see how that can be. So if this is a fraction of a frame, then if I multiply by 100, this kind of gives me the percentage of a frame. And this is the thing that I want to print out. But first I want to just convert that to an integer. So I'm going to call the floor method. Math.floor, by the way, is just part of Lua itself. This is not something that MAME added. You can go straight to the Lua documentation and find all of the methods that you have at your disposal. And this is the value that I'm going to put in my captured time variable. That's the thing I'm actually printing. So we're getting close, but we're not quite there yet, because this is just going to set the variable once on initialization. What I really need to have happen is for this line to be called every time we hit that breakpoint at A1, B1. The classes exposed to Lua do include the debugger classes, and that does include things like breakpoints, but I have yet to find a way to actually use this in a useful way. For example, I can't have an event that says a breakpoint has been triggered and so run my method at this time. This just seems to be a very straightforward exposing of the internal debugger class from MAME, but not in a way that lets me subscribe to any events. Luckily, there are events on the memory class. In particular, I can go into a memory space and install either a read or a write tap. These are kind of like watch points. This allows my method to be called whenever a certain address or a certain range of addresses is read from or written to. Now, I initially thought, okay, whenever we read the instruction at A1, B1, that's where I want to install my read tap. But somehow that doesn't quite work. There might be something odd about the fact that this is ROM, but for whatever reason, that read tap did not work for me. But there was a simple alternative, which was I could install a write tap, not to this address, but to this address right here. This is the console.in buffer flag. So whenever we clear it, I could set a write tap here to know that it's been cleared, and that happens just before we jump to A1, B1. And there don't seem to be any other places where this is written to, at least not many places. So this is at hex 70. So ultimately I'm going to add this line here, but this is going to require a bit of plumbing for it to actually do anything. But I'm going to go into the memory object. I will install my write tap, beginning and ending at hex 70. That's that synbuffle flag. I have to give this handler a name, and then I actually provide the name of the function that will get called. So my first bit of plumbing I have to do is I actually have to define my mem variable. I can define the mem variable based on the CPU. So after the CPU has been defined, I can go into the CPU's spaces, I can go into the program space, and that provides to me the memory space for the program running on my CPU. The next thing I need to do is actually define this function. So I give the name whatever I like, but I always have to have 3 parameters. because when this gets called by the system, it's going to tell me the offset of the address that was actually accessed, the value of the address, and the mask. And you can learn more in the documentation about what those 3 parameters are. I'm actually not even going to use them. I just have this as a container in which I can put my new piece of code. So now whenever hex 70, the address, is written to, I will update my variable captured time. I will update it to be the time it takes to vblank in units of a percentage of a frame and converted to an integer. And then when it comes time to draw the overlay, which happens every time the frame has been done drawing, I'll have this variable that I can print. This is not going to work, but let's watch it crash and burn so we can learn something. The error that I got was at line 13. I'm attempting to concatenate nil. So nil is a special value, it's a special type in Lua, and it isn't anything else. It's not a string, it's not a number, and you don't want to go around printing nils. So I'm just going to initialize my captured time up here to be 0, so it is not nil. This is still going to crash and burn. Let's watch. It looks like it's not crashing and burning. Oh, it changed a bit. Okay, cool. Now let's start typing. And it doesn't change. There is no change. Why is it not changing? The answer may surprise you. When you call install write tap, it returns to you an object that represents the handler that you just installed. If you don't put it into a variable, my guess is that that object gets garbage collected and then disappears, and you no longer have a handler anywhere. Let's try it now. Aha! Ha 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 ha! Look at that. Okay. So now we're getting some performance statistics that would be very hard to do directly from the CoCo itself, and only moderately hard to do from Lua. Just for fun, it could be interesting to print the value of the cursor character and have that also update itself inside that bounding box. So what I can do is I can use this cursor position variable in the ROM. This gives me a pointer into the screen memory, and then I can grab the byte at that screen memory and print that. Curpos is a pointer at hex 88. So at the top of my overlay function, I can add a way to get what's sitting at 88. I go into my memory space object, and it has a method on it exposed by MAME called readU, and there are a bunch of actually different variants of that. This will read a word, unsigned, and this is the address. So this will give me the 2 bytes at 88, and that gives me the pointer into screen memory where the cursor character lives. I can then use the cursor pointer as a parameter to yet another read method. So I go back into my memory space object. This time I just read a single byte, and this time the location I'm reading from is cursor pointer. And I'll put that result into cursor char. And just above the % frame remaining, let's print that. This will print the word cursor char and then the value of the cursor char variable. So now you can see this is going up through the colors as we see here it going up through the colors. And as I type, the % frame remaining will update itself. And you'll also see that the cursor char goes kind of a little wild because it keeps resetting to, I guess that's orange each time. And then if I stop typing, then it gets a chance to cycle through everything. Well, that covers it for this video, but I am not done. I want more. I want some flashy animation. I want some moving meters. And so next time we're going to add a performance meter. Until then, thank you for watching.